Okay. So, actually, I'm gonna pull up. I have it up. Perfect. Just a moment. Okay. So I guess just to start off, I know that this week or last week was one of the harder weeks. So going forward, it's a little bit easier, a lot bit easier. So just a reminder, we only have 2 more weeks of this course. So we have this week and then all of next week to finish the rest of the content, and then it'll be the end of the course. And yeah, hopefully it went by quickly. So I will say, just to proceed with what we have ahead. So week 5 was what we just did. That was with the complicated diagrams and all of that, which I'll touch on that a little bit today, but I won't touch on that too much, just because really this is the only week we ever deal with combination circuits. And then if it makes you feel better, I know that this is definitely one of the harder weeks, especially dealing with the voltage drops, which I will try to send a little bit of a diagram out that kind of explains how you get the answers for. I can't give you the answers to the quiz, but I can at least explain a little bit more about how you calculate those voltage drops, because it can definitely be confusing. At the end of the day, it's really just like creating a puzzle and seeing what you can find, calculating it, and then eventually you're going to be able to calculate more and more things the more calculations you do. But I'll send a few more resources on that I find helpful. So that was last week. So looking at this week, so there were quite a few videos on voltage dividers, which I'm primarily going to touch on. I guess not just touch on, I'm going to do the examples that you have to do for the quiz, just because I figure if you're here, you might need help on it, and I appreciate you being here, and if anyone listens in the recording. So we'll go over that today. So again, electrical quiz 8 is something that essentially you have to design 3 different circuits, and they're kind of using the principles from last week and this week. So if you were a little confused last week, this might help. This week might actually be a little bit easier, and it might kind of help you be able to work backwards and understand anything you didn't understand last week. So that's what you have to do for this week. That electrical quiz 8, you can, like it says here, if you want to do it in Microsoft Paint. I think that's kind of difficult, so most people just do it on a piece of paper, write it, label it 1, 2, 3, and you'll be good to go. So that's a reminder on that. And then week 7 here is really quite simple, so that's a plus. So there's only 2 lecture videos, and they're very, very straightforward. There's not a lot of math involved. So I think next week we will talk about like conductors versus insulators, and then the American wire gauge, and then we'll show some charts, and it's going to be a little bit more real life situations, and the questions they ask are more qualitative questions, so not quantitative, meaning there's not a lot of like math involved in next week. So this is really the last week that math is involved, so that's a plus. But yeah, so I guess just to touch on last week's before I dive into week 6 here. So week 5, and a lot of people had trouble finding these voltage drops, specifically on the second one. So I'll send I'll send some resources on this, but all in all, my biggest hint is, first, when you do this, once we got down to this, and I know I'm jumping right in here, but again, just touching on last week. So if you're not following it, that's fine. But last week, we basically showed how we condense this combination circuit into this simple series circuit, and determined that, the total resistance was 10 ohms, right? Because once you got it in a simple circuit like this, we could just add 4 and 6 to get 10. The reason that is such a critical step for the rest of solving your circuit is because that allows you to solve for this key thing here, which is the total current. So That's always how I kind of start these. Is first I find, we're given the total voltage. You find the total resistance, and then with that you can find the total current. That doesn't solve the rest of your problem, but it can allow you to basically, with this information, start kind of filling in some of the unknowns here. So when looking at this combination circuit and this large circuit here, essentially what we're doing is we're calculating what the voltage, what the current, and what the resistance is at that given point in time. And for example, for like, given the fact that we know that this is 0.5 ohms here, we know that 0.5 ohms is going, that's the amperage right here, right? Because that's the start of the voltage. So the start of the circuit here is 0.5 amps, which also means that the start of this circuit is 0.5 amps. The start of this circuit is 0.5 amps until there's a point where that current is going to change direction. So like in this first one, it's 0.5 amps all the way to here, and then we know it splits. The second example here, where we condense it further, it's 0.5 amps all the way to here, and then it splits, and then it changes. But with that, when we know 0.5 amps is here, we have this one solved for R1, because we know what the amperage is, we know what the resistance is, so we can find what that voltage is. And that's really all this is it's just kind of working backwards and, going from there. So like the way that I would, one of the biggest steps I would do first is once we calculated that total current, you can go back in on the simple series circuit and know, okay, well, if we know that 0.5 is what we're starting with, we can easily calculate what the voltage is at this 4 ohm, because we would just do, V divided by R, which is 2 divided by 4, which 2 divided by 4 is 0.5. So that means that we know, I did that backwards, but same thing. We can calculate here the voltage, which is what I did by doing I times R. So we knew that R was 4 ohms. And we knew that I was 0.5 ohms, because that's what we're starting with. So that's how I calculated 2 volts is the voltage drop there. And then once you calculate that, you can kind of go back through and say, okay, well, this is we know R1 is 2 volts. So I just filled it in here and I filled it in here. And then you can do the same thing for that 6 ohm, just, 6 times 0.5 again, because I knew that that's the current going in there is 3 volts. And then you can kind of work backwards and solve that. So that's just some advice, and if that's still confusing, we can like I said, I'll send some resources that'll be helpful, but ideally I would look back at this, because this is the most helpful to just remember these concepts of, a lot of times once you do the calculations to find some of these voltages, just by theory of things being wired in parallel, you can tell what the voltages are there. So if you remember back to this first example that we did, R3 and R4, which were, these two that are wired in parallel, we determined that the voltage between those both was 15.3, but that meant that the voltage of R3 and R4 alone was also 15.3, because anything wired in parallel is the same. Likewise, looking at this, anything wired in parallel is the same, which means like when we condense this down to this 4 ohm and this 4 ohm, it means that the voltage here and the voltage here at this 4 ohm are the same. So really, it's a lot of the same ideas. Likewise, with amperage, looking at R1 and R2, you can see here the relationship between that as well. So just wanted to point that out, which might have accidentally typed in the wrong. Yeah, I did type in the wrong things here. It should be, but that's what I'm confusing.
I guess I can do this in my sleep. I mean, it's not real complicated to me, except for that bigger drawing like I emailed you, I guess.
Mm-hmm.
I don't know how to split. I don't know what voltage to give the the 10 and the 2 when you're over. I guess in your drawing that's showing the 2 volt only and the 3 volt. I understand that the 3 volt's going to be there all the time, all the way through it. It's there, but until the last picture it gets split. or the first picture, I should say, it gets split.
So
But the 10 and the 2,
that's confusing part, yeah.
it's
So-
like throwing me off. I don't know how much to give each one. That's what I just had to guess on the quiz because I had no idea.
No, yep, it's definitely hard, and this is where it can be confusing. In the video, it's kind of hard to follow because it's hard, I think, to do this section, this tiny section. Like I think this class, all in all, it's works pretty well in an online format, except for this week and this week and last week, of course, when we're drawing all of these circuits and you just see all these numbers everywhere. It's hard to follow. Like in the video, if you watched it, I had to watch it a couple times just to like grasp, because I want to make sure I'm explaining it the same way they're explaining it in the videos. And, it was difficult to kind of grasp. So what they do is, if you've noticed throughout the video, he's using 3 different colors. So he was using, which let's just, I'm just going to pull that video up to just, because I think that's the most helpful part. And I know this one was a hard section, so I'll get to this week soon, but I think that this is an important piece to
It's number
touch.
3, yeah.
So I'm just gonna fast forward here.
He splits the 200 into, or the 50 volts, he splits it 3 ways.
The 50 volts you're talking about, sorry, there's a lot of 50 volts. Which ones are you talking about? This
Okay,
one?
yeah, up there, over to the right, up there, straight up.
This one?
That 50 volt, he takes down here to the picture at the bottom with the 3 stack up, yeah, right there. He splits that 50 volts with those 3 resistors. Or he splits, yeah, he splits the 50 with them. The 100 gets 25 volts and each 50 gets 12.5. Is that what you're gonna tell me, or?
No, so what I was going to say, and the reason I
I'm
wanted
sorry.
oh no, you're totally fine, because yeah, that was a good like thing to pick up on. Yes, he does do that, but more at large is when he's doing this, he's using 3 colors: black, blue, and red, right? So blue he's using
Right.
for amperage, black he's using for resistance, red he's using for voltage. And if you'll notice, he's not solving all the volts and then going back and solving the amperage. So he's doing what he can at the time. So for example, when he calculated that this was 0.5, that allowed him to calculate that 25 volts, right? And if you look at where you're stuck here, so there's maybe a idea that you might be forgetting, because it's easy, because we did this a couple weeks ago, and so it's easy to forget. But one other thing, so we know that this right here is 0.5 amps, right? This right here, this 2 volts, and so we know 0.5 is going here, and we know it splits up here, right? Well,
Right.
since we know what the resistance is here and the voltage here, we can calculate what the amperage is there, which means
It's
that we can
0.2.
by default know what the amperage is here, because we know that where it splits, it always equals what it was at the beginning. Remember that rule that we did where, like, if you have one current going in and one going out, what's the other one? And
Yeah.
so we could calculate amperage there, which means we could calculate voltage here, right? Because once we get amperage here, we can calculate voltage there. So sometimes it's not always like, even though the questions might say calculate voltage drop, by theory, when you're working through this, you might have to calculate amps first and then go back through and calculate voltage drop. So that's probably what can get confusing. But that's just something to keep in mind. And that's why in the videos, again, like, just at large looking at this, he's writing in these amperages as he's going, because they're allowing him to, determine later on other values. So like this situation here, look at this one being 0.25 here. Reason he wrote it here was because he knew that, okay, if your electrons are going around here, they're going 0.25, this whole thing is 0.25, right? Because
Right.
it's, there's nowhere that it's splitting, which now knowing that, you can sit here and calculate the voltage here, even though they're not the same, we know current for that situation is the same. So that's why it's just the rules, and I tried to say this a lot, but the rules that we learned about like voltage being, how it is the same depending on if you have parallel and series, and learning about how current splits in a parallel circuit, all of that comes into play, in little pieces like that. So it all ties back in, but that can make it really challenging. But yeah, I'm gonna jump into week. Hopefully that helped.
Yeah, it did a lot. Thank you.
Yeah, of course.
I
And
mean, I I'm probably gonna redo the quiz and see where it comes out, but I had a good score. I just wanted to make sure I understand it, because
mhm.
I actually asked some people that were already doing this kind of stuff, and they thought it was a trick question too, because like you said, there's a bunch of electricians that actually don't know anything about this stuff. They just use their voltmeter all day and they're good.
Right. Yeah, that's the thing. That's the thing about like all of this is there's two different sides when you're learning you know electrical, any type of electrical concepts. It's you've got the math and the reasoning behind it, and then you've got the real world applications. And the real world
Okay.
applications is what you learn at work, and the math side of it's what you learn here. So
Because like in real life, I mean, you could just test those
exactly, yeah, you
circuits
wouldn't have to do
and
this in real life.
and it would tell you what the drop was or whatever it was, right? And so that's what this guy, I was talking to, he knows how to do all that, which I don't really know how to do that part of it. But he's like, this can't even be done. And I'm like, I know it can be done, dude. It's not like they're gonna give me something at college that can't be solved. I mean, it's
Hopefully not, unless there's a mistake.
like there's some kind of a misprint. But okay, we can move forward now. Thank you.
Yeah, of course. But yeah, no, it definitely that week is challenging, and so is this week. But next week is a little bit more easy. So next week is a lot easier, you'll find. So that's a good thing. So basically the main idea from this week, I'm just talking about voltage dividers. And voltage dividers, this right here is really kind of like the general look of a voltage divider, kind of like we have a general look of a circuit, right? That's just a typical voltage divider. So you can see here that we're introduced to a couple more ideas, and that is this idea of V in, which is the voltage at the battery, and then V out, which is essentially in this like second half of the circuit there. And then we're given two resistors. A couple things to note about voltage dividers and the way that we're designing them and drawing them is that R1 and R2 are always in this sort of configuration where we have R2 directly parallel to V out, or sometimes this might not be called R2. So I should just say you have a resistor directly parallel to this V out, and then this other resistor directly out of that. So it kind of looks like a combination circuit, right? Because we have a series component in this larger portion, and then we have a parallel component here. So that's why we did combination circuits last week and voltage dividers this week. So basically, I have it written here, but just to read it. So voltage divider, it's just a simple circuit which turns a large voltage, so this V in, into a smaller one, this V out, using two series resistors. So these are wired in series, R2 and R1, because there's nowhere that current splits between them, which can look tricky because it's easy to say, well, current splits right here, right? But no, because of the way that the battery is flowing from the negative side to the positive, because electrons want to get to the more, electrons, just the way they're designed, are attracted to the positive end. So the circuit's flowing this way. So the circuit, or the electrons, don't have two paths to go here. They only have one because they're moving. They have two paths to go here. Some go this way and some go this way. But between R2 and R1, there's only one pathway. So that's what it means by wired in series, with what it says here. So you have your input voltage and your output voltage, and that output voltage is just a fraction of the input. So for example, in this video, he shows like, okay, we have a simple circuit here with two resistors, and there's that large voltage here, and then the resistors have a voltage that's a fraction of what that voltage is. And the reason voltage dividers are important this week, we learned, is that if we utilize them correctly, we can essentially design a circuit for whatever our demands are, which is what we'll do in these last two problems that are on this week's exam. So we're also introduced to this new equation, which is written here. So V out equals V in times R1 over RT, where R1 is just denoted as whatever resistor you are working with. So basically, an example of how you would use this equation here is shown in this circuit right here. So in this circuit, we have our 24-volt battery, which we know, like I said here, that's your V in, which is your battery. We were also given two resistors, one at 200 ohms and one at 500 ohms. So all of that is enough information to essentially use this equation here and calculate what V out is. So we have 24. So to do this first one here, and again, I'm doing this at this resistor. So we have V in, which is 24, which is our battery, times 500 over 700. And the way that we got this portion right here is we did the resistor value, which was 500, divided by the total resistance, which was 700. So 24 times 500 over 700, or 24 times 5/7 is 17.14, which means this here is V out at the R1 location. And again, we know that the RT here is 700 because looking at the circuit we were provided, we can see that it's wired in series, which means that our resistors, we can sum together to get the total resistance. So you can also calculate the voltage drop, which is, V out is also called the voltage drop. I guess I should have said that earlier. At this location here, it's the same thing, but instead of having 500, we have 200, and that's because 200 is our resistance value here. 700 remains the same because the total never changes, right? It's the total is here. So really when you're, it didn't matter how many resistors we had in this, the only number that ever really would have changed is what that is, because that's at that specific point, or the R value at that location. So again, that's just an equation we were introduced to this week. Doesn't really come up too much throughout the remainder of this course, but just important to know for future courses and applications. Okay, so one of the first videos they do, and the videos can be a little bit confusing, so I like to normally just screenshot it and walk through it again. So in this video, you can see here that this looks exactly like that voltage divider situation. We had one resistor parallel to that V out and one outside of it, which is exactly what this looks like. Typically, this V out is, it's voltage, so it means that we have some sort of load or something there that we're trying to wire. In the examples that they do, it's usually just a light bulb, since that's, the most generic load we see. So this is, again, something that we want to give power to. So in this example, they gave us that we had a voltage divider situation with a 24-volt battery. So that's what's given here. And he drew here in blue the arrow locations, which you should already know, right? So, our electrons are flowing from the negative end here. Some are going to go this way, some are going to go this way. And then they meet back up here and then loop back around to the end of the circuit. We were also given the parameters for the load. So we were given that in order to power this load, you will need 12 volts and 100 MAs, which is, 0.1 amps. That's all we were given for this problem, was these two values and this 24 volts. But that in itself is enough to solve for what R2 and R1 equal, which is the point of this question and the point of, really the point of this week's exam. So this in the corner here is something important that is critical for designing these circuits for this week that we're introduced to, and it is the idea of the bleeder current. So the bleeder current, by practicality, means the current that is not going to the load, and typically that's around 10% of our current. And it makes sense if you think about it. So just looking at this from a practical sense, we have, some electrons, so we have some current going this way, right, down this pathway. So some electrons are making this exact path, this square. Some electrons are not doing that square, and instead right here, they're going here hitting this load, so lighting it up, and then going around that way. Well, obviously we have some current going in both of these pathways, but it's going to be different. And that difference depends on however amount of current we need for this load. And typically you would want the majority of your current to go to that load, right? Because, I mean, you know, depending on your application, but for the most part, you would want the majority of your load or of your current going to that load, because that's, you know, the whole point of your circuit is to light whatever's in that load. So, again, we were given this, but knowing this information that a bleeder current is approximately 10%, we can also determine what the current is here. And we can do that by just taking 100 MAs and multiplying it by 0.1 or 10% in decimal form to get 10 MAs as the current here, or 0.01 amps. And again, we know that because it's 10% of what the load is. Okay, so with that, we know that all we calculated with that 10 MAs was the current right here along this pathway from this node to this node. And that is because right here, once the current changes again, because now we have a connecting piece, right? Because we have 0.1 amps here, and we already know that this is, or sorry, no, we have 10 I'm going to use MAs because that's easier to pronounce. We have 10 MAs here, and we know that we have 100 MAs here, which means that this node right here, they're going to combine and add together to 110, which means that the current, so kind of going through this current again, it means that, and remember, whatever you end with and whatever you start with are always the same. So that means that we have 110 current, we have a speed of 110 here. At this first node, we calculated that 10 goes here, 100 goes here, and then they meet back up to form 110. And all of that makes sense because it also makes sense that we had 110, you know, going in here, 10% of, you know, that load is going here, and the other majority of it is hitting that load. And that kind of brings that idea back to life of, you know, Kirchhoff's law, how we have these nodes and we have the splitting of these junctions where we have the splitting of current and then the combining of current again when we meet up again. So that was really the bulk of this problem, was developing or determining what, you know, your amperage was at every given point in the circuit, but that wasn't the question. So the question asked for resistance, which we can easily find the resistance at each of those resistors because we know all of the unknowns. So we know that it is 12 volts, and I'll explain why it's 12 volts here in a minute. But for R1, if it's 12 volts, we would do V divided by I to get R. So 12 volts divided by 0.01 amps, which again, we know it's 0.01 amps because that's the 10 MAs here. And for R2, it's 0.11 amps because that's what our amperage is right here, which was 110 MAs. So how did you calculate this 12 volts? Well, you calculate that 12 volts by a couple different things. One, whatever that load is, since it's parallel, it means that the voltage is the same. So we knew that this was 12 volts, R1, because the load needed 12 volts. How we calculated R2 was we also know that the voltages have to add up together. So if this is 12 R1, that means that R2 is also 12, because 12 plus 12 is 24, or 12 minus, or 24 minus 12 is 12. So that's how we found the 12 volts here. And then that's how we found the amperage here to be able to use Ohm's law to determine what our resistance is at those particular points. Now that was a mouthful, but that's really the bulk of what it is. And just a couple, this is a lot of words on one slide, but just to summarize some of the key things in that last slide that we were told. So, you know, the fact that we were able to solve this circuit because we were given what that total voltage was. You know, in this example here, the idea was we're really just solving a puzzle, right? We're looking at one piece, figuring out what we can solve for, and working backwards to solve everything else. You know, it's important, this idea of that splitting current, like we talked about in past weeks, it comes back up, and that's how you solve these voltage dividers. When you're doing these voltage dividers, you're always going to be given what parameters you have for that particular load, or you're not going to be able to solve the voltage divider. That idea of that bleeder current is what you needed to solve that problem, right? So just make sure that this concept is clear for how to use this 10% value in order to calculate the, particular amperage that you need at whatever point in time. And then, this last bullet here is basically just saying that all in all, once you solve the circuit, you should be able to look back at it and it should all make sense together, right? Like this makes sense when we look at it as a whole. Like we have our two resistances, which have a voltage drop that equals what the total voltage is. We have, amperage that makes sense in our load and also makes sense when we combine it back together. So just an idea, to go back and look at your circuit and make sure it all makes sense. Okay, so now we're going to kind of hit at the problems for the quiz, and again, just send it via email. So this is the first problem we have, and this one's really easy to do. So we were given that we have a 12-volt DC battery here, and we were also told it was a series circuit with 3 resistors that divides the voltage into 2, 4, and 6. The total current of this series circuit should be 100 MAs. Draw a diagram, show each of the value at each resistor. So this is the first thing you should have been able to do. So we know that we have a 12 voltage circuit. We know that there's 3 resistors. We know that the voltage drop at each of those resistors were given, but we don't know what that resistance value is. But this tells you how to do everything. This 100 here, because we know that this is a series, so we can just quite literally use Ohm's law, divide all of these voltages by 100 and be able to determine, what is our resistance. Just note that it's in MAs, so you can convert it to amps if you want. But that's all this was showing you, is that, Ohm's law is important each week. And this is just a simple example. It doesn't really relate to the voltage dividers in particular. This more relates to kind of the earlier weeks. But yeah, so that's how you would do that first problem. I'm not going to solve this one for you, but again, you can do it by just taking these values and dividing them by I, which we know is 100 MAs. Just make sure that you convert this to amperage first, or technically you'd have, I don't think there's things such as, I don't know if there's milliohms, but I don't think that would be the proper term. So convert that to amperage first. Okay, so this second example that's on the quiz is exactly like the one I just showed you. So in this example, we have a 24-volt power supply, which is again your battery, and we're given the parameters for the load that we want to light. This one's a little different because now we're given that we have 500 MAs and 8 volts, whereas this example here was 12 volts and 100 MAs, but it's the same principle. So the first step, just like we did last time, we can calculate that bleeder current by doing what the load is here times 0.1, which is 10%, which means that we had 50 going in here, right? Which means we had 50 going into R1. With that, we can calculate what R2 is, right? Because if we have 50 here and 500 hitting this load here, it means that when those two pieces meet back up at that junction, they add together, right? So 500 plus 50 is 550. And that is as simple as how you solve this one. So once we have the current and the current, we can solve the voltage. And we can solve, or we can't solve the voltage, we can solve the resistance at that location, because we can solve the voltage. And we can solve the voltage because if we know this is 8 volts, we know that whatever's parallel to it is also 8 volts, which means I can write 8 volts here. That's not an 8 volts. And we also know that these two voltages have to add up to 24. So you can easily, 24, subtract that 8 and get what the voltage is here, which is 16. And again, at 16 plus, because 16 plus 8 is 24. And then with those two values, now we know voltage, now we know amperage at both of those locations, which means that you can use Ohm's law, which is, again, here, R equals V divided by I, to solve it. And I didn't send this PowerPoint just because it basically has the majority of the answers in it. So I was afraid that I would get submittals that were just this. So feel free to, copy this as I'm doing it. But yeah, that's why I didn't send this if you're wondering, because it basically goes through the answers. But really the only thing left for this, looking at this right here, this is almost complete. Just the only thing you'll have to do on your own is calculate the resistance value at R2 and R1, which again, you can do very simply by using Ohm's law and using these two values that we already calculated. Okay, I'm just gonna pause because I guess I'm going through this quicker than I thought, but does this bleeder current when you only have one load, is this pretty straightforward, or just make sure that,
Yeah, I think it's pretty straightforward.
okay, perfect. Then I'll move on to the more difficult one, but definitely I talk fast, so stop me if it's if I go too quickly. So the last problem for this week is a little bit more complicated, but once you get the hang of it, it's not too bad. So in this situation, we are given two loads that we have to, have our voltage divide into. And so basically to kind of work through how you would design that. So just like the last two, it was a 24-volt power supply. So that's what our battery voltage is here. So we were given that we need two loads to be powered. And this is always going to be the typical setup for when you have two loads and a voltage divider when you're building these circuits. So you're always going to have one series component here, and then the voltages kind of split into two different circuits here. And the smaller load is kind of embedded in that bigger part of the circuit. So this, I guess just what I mean is when you have one load, this is what a voltage divider looks like, this configuration. When you have two loads, it always looks like this configuration, just of course different numbers. But okay, so we were given that the first load requires 4 volts and 200 MAs. The second load requires 10 volts and 300 ohms. Okay, so what that tells you is the smaller one here is in the smaller circuit. So we know that that first load, which again is something like a light bulb, is 200 MAs, and we're also going to write 4 volts here, which also means that the resistance that's directly parallel to that is 4 volts, right? Because 4 volts and 4 volts are parallel, so they're the same. We were also given that the second load here is 300 MAs and 10 volts. And this is where a lot of people make the mistake, is they put 10 here. But in reality, even though this 10 volt and 6 volt is parallel, you have to consider that we have this 4 here too. And this, it kind of goes back to that combination, these 4 and 6 and this 10 volt, they're in the line together. So these two are parallel to that one. So this is why we knew this was 6 volts, and that is because it had to add to get 10. So 4 plus 6 equals 10. So we were given again that this is 10. We determined this is 6 by looking at this and subtracting the 2 and finding the difference. Okay, so that was the hardest part. So it was again determining that this was 6. And just quick, we can determine that this last resistance is 14 because they all have to add up to 24. So 14 plus 6 plus 4 is 24. So now we have all of the voltages at all of the locations. So it's just going back and finding the amperage. So what we knew is we were only given this 200 and this 300. But that means that where those two split, which is this location that I'm going to put a circle around because it's kind of confusing. So this is the part that those 200 and 300 split up, right? The current. A lot of, it's not this location here because this is the same pathway. Right here at this location, some electrons are going all the way around here. Some are just going like that, but some are going all the way here, stopping, hitting this load, and then going like that. Some electrons are going all the way around here, not going this way, and instead going this way and hitting this load. So at this location, we have it split to 200 to 300, which means, and like we talked about at the beginning, it adds back up at the node, but it also means that before it splits, it's the sum of both of those. So that's how we determine this number right here, this 500, because if we know this is 2 and this is 3, we can add them to get 5 because we know that that current has to split here. So the last and final piece of this, and probably the easiest piece to mistake here, is right here. So a lot of people see this as 500 and they're like, okay, then this is 500, but no, it is not. And that is because this point right here, there is this location before it where our current splits. Right? But we can determine this 550 because a couple different things. So we could determine that this was 50 MAs because we have no, just kidding. So the way that this 500, this is the easiest, probably the easiest way to explain it. The way that this 550 got found was just back to that bleeder current idea of 500 times 1.1. The reason that this says 1.1 and not 0.1 is because if we know that 10% has to go, or 90% has to go here, it means that this right here is 10%. So you could do 500 times 0.1 and get 50 and find this, and then go back and find this 550, right? Because 500 plus 50 is 550, which is where they split beforehand. Or you can just know that that bleeder current is 110% prior to the split, right? So you can either calculate, you can do 1.1 and calculate before the current splits, or you can calculate this resistance 1 value by just doing 0.1. It's again, 500 times 0.1 is 50, or 500 times 1.1 is 550. Does that make sense? Why this is okay? Just make sure, because I don't know if I explained that well. But okay, so if we know that this here is 50 and this here is 200, we can calculate that this section just from here to here is 250. And we know this little path is 250 because, again, this 50 and this 200 meet up, add together to get 250 here. So this was why this one is a little bit tricky, and it's because you kind of have to treat all of these circuits as individual circuit components, until we get to the whole circuit solved. So once we determined that this was 250, you can look at it again and see, well, if this is 300 MAs coming in here and this is 250, it has to add to 550, right? And that is our check that we did this all correctly, because this added to 550 and this added to 550, right?
So it's 0?
No, this is the current. So the current, if you remember, the current at the beginning and the current at the end is always the same. So we know we did this correctly because the current starting going off of this battery is 550. Of course, it changes as it goes through the circuit, but all in all, in the end, it adds back up, and the current is the same speed that it started with, the 550.
Oh yeah, I was talking about the 14-volt resistor thing at the top.
Oh, the 14-volt resist. So this 14, it's not a 14.
Or 14-volt, whatever it,
So
power supply or whatever.
Yeah.
Is it? How can you, I mean, when the 300, I understand the 300 comes around
Mhm,
and then it hits that junction where you're at right there,
mhm.
but it's already meeting up with 300, isn't it?
So this 300 here is meeting up with 250 to get.
Oh,
550.
250.
Yep, so 300 plus 250 is 5. So when you're calculating the current, you only combine the two lines coming off of that junction. So you don't have to worry about like looking at this and that. You're only looking at the two that are directly coming off of it. So 250 plus 300 is 550. Just like right here, the two lines directly coming off of it were 500 and 200 to get 250.
So what's the mistake that people make when they
So
get to the end?
the mistake that people make a lot of times is they forget that this piece here is 250 and not 50.
Oh,
And they just do 50 plus 300 and think this is 350, and then it doesn't add up to 550. So this is the hard portion. The fact
I
that we
see.
had to divide it twice. And
Right,
now,
the reason why you have to, the lower one that has the 200 MA,
mhm,
it is in parallel with the one that it's connected to so that it gets the same voltage,
mhm.
but the other one does not get, the other one is in series, so you have to add the two.
So the way that we got this 6 is, and this is where
Or I
the,
mean, sorry. Go ahead.
oh, sorry, I didn't mean to cut you off, but yes, we did 6 here because we knew that this was
That we
10
already, yeah, we
and
already knew
6,
that one was 10, so,
6 plus 4.
all right.
And then once you solve all of it like this, the last step, which I'm not gonna do, but the last step here is that we can solve the resistors, which is the point of this, right? Because we know the amperage and the voltage at both locations, because we know 250 and 6 and 50 and 4. So you can, just like the last few, use this equation and solve what those resistors are. And you can solve it here too, because we have 14 and 550.
Right.
So yeah, this week, I would say this week's, I think this week's easier than last week.
I think it is a little bit easier, but it's the other one is a very, very tricky puzzle. Like I was pretty, I struggled with it and I reached out. That's why, you said reach out if you need help, because I'm like, I'm not doing it right. But I get where you can fill in, different numbers and see what you get, but I just couldn't come up with the right numbers to meet up with Ohm's law. It would fail every time. Like it didn't matter what I did, it would fail. So I think I got a better idea now, so I appreciate it.
Oh, of course. Yeah, I'm glad that helped. Yeah, sorry. I don't know if I don't think I responded to your email, but hopefully I addressed it here. But if there's any other questions, definitely reach out again. And if I don't explain it in the, week in next week, 'cause that's last week, just send me an email and I will try to explain it through typing. But this one would have been hard to, it was easier to visualize, which is why it was probably best to talk through it like this. But yeah, so just submit this, and that is once you do this, you just have, make sure you keep up with your Amatrols, and just make sure also when you go into your grade book, which you should be able to access your grades by this grading tab here, make sure that you have for all of these are what I mean by Amatrols. Make sure that you have grades for all of those that you have
Yeah.
completed, and also make sure that you do this program of pathway guide acknowledgement, the student success quiz. So if you go to grades, you can just click on them and it should
Yeah, I've
open,
done all that.
and the course requirement. Okay, just because those are 3 that it still looks like quite a few people haven't done them. So
I've been meaning to ask too, like, this textbook, it's so deep. Like, I mean, you could teach this class for like a year, I think.
you
It's like
could.
that book is so much. It's like, wow, you could like just read that, and probably if someone just would show you how to do half of it, you'd be really good at this stuff. But with this course is so fast that you don't really have time to do it all.
I completely agree. Yeah, I find that's the hardest thing with any college course, and taken quite a few college courses in my life, and I'll be honest, like when I ever had hard, challenging engineering courses, that was the way I learned. Like you don't always have like a teacher who can teach it correctly, which is or teach it in the way that you understand it. So sometimes sitting down and reading that book it takes a lot more time, but it's the easiest way to learn everything because it's a lot more comprehensive than someone could teach. But at the same time, like you said, it's a lot to sit down and read, which is why I say for this course, I think it's a good supplemental for like this, subjects or the chapters that you're struggling with. It's a good thing to maybe sit down and read it, and then ask questions. You might have a better grasp or understanding. but I don't think that it's it's not a requirement of this course to sit down and read it, because quite literally, I don't think there's enough time to sit down and read that
Right.
book and watch all the videos and do the math and electrical portion. So,
And another thing I was wondering too, which is sort of like off, but where is everybody? Like nobody comes to the class, to the Zoom. Are there very many people in this class? I mean,
well, I think a couple of things. I know that I do these late. So one, I record these so I can see who watches the recording. And that's why I send the link typically. So a couple people watch the recordings. But also I guess some people, either if they don't watch this video, then they watch all the other videos and understand it, or I guess some people don't care about what grade they get in this course and just want to pass the assignment, pass it enough to, move on to the next course. So I don't know. Yeah, I don't get a ton of participation sometimes, but I think that's what happens when you don't make participation a grade. Like I know some, a lot of times, there's teachers have like participation as a grade. I don't, because my thing is, if you don't need to listen or don't want to listen to the video and you just know it, then you shouldn't have to sit down.
Right.
But I think it's
That's cool.
important to also, I think interactivity is how you learn. At least some people, that's how I learn. If I need to ask questions to a real live face, I can't always rely
Right.
on text. So yeah, a couple different things, but this is pretty typical. A lot of mine, especially being late, I know a lot of people work second or third shift, so time doesn't work. But I appreciate you being here. It's
I
and I will
appreciate
say,
you being here.
this is my job, so I've got to be here.
Right.
But, I will say too that I do, and I try to say this at the beginning, hopefully I did, but for those that like participate actively, like are in these meetings or watch the video, if like there's a borderline in your grade where you're very close to that, next grade point average, I normally do bump you up, a percent if it's gonna give you a better grade, because I think participation is important too. So
Sure thing.
so
That would be great.
yeah, but because I also think the grading scale is a little challenging for this course. And 94 is a 4-point, I think, how it works, which is crazy. But yeah, so that's all I had today. Like I said, next week will probably be
Alright.
pretty short because it's a lot simpler than this week. So that's something to look forward to.
All right, well, have a good night. I'm gonna just watch all the videos, lectures and stuff at my own time. Like, I don't have time tonight, but
Yep. Sounds good. And yeah, reach out
Yep.
if there's any questions or concerns. And yeah, one more week of this course, and then you're on to the upper level ones, I think, after this one. So
I actually, I'm gonna go on to it, not this next semester or whatever. Probably next semester I'll go to it because I took a different class. I took a fluids and electricity class
oh, okay. What number is
instead
that?
of
ELT is
huh?
what number is that in ELT?
Um just sec.